Welcome back to ECE 220. 2 days away from exam number 2. This is ECE 220. A lot of 2's going on. I don't know why that came to mind, but hopefully you remember in 2 days our exam number 2 will occur, and we have material that has been added to. A little additional material for exam number 2 will be phasors, so please make note of that, and we'll go through some of that today, hopefully to get you a little more comfortable with playing with complex numbers. And the idea is to get you ready for chapter 9 when we really have to use it routinely to be playing with complex numbers. That's the idea. We're talking today about chapter 6, and we'll try to finish up the inductor piece. Then we will take a detour and get into chapter 9, which is the phasor material, so you'll have some more exposure to that before we get into exam number 2. Homework 7 is due tonight. Group B, before that, you will have lab number 2 to attend. That's section I. Group A, your lab number 2 report is due tomorrow. And your group A, you will have your pre-lab for lab number 3 due on Saturday. I need to make sure and give you the drop box for that on D2L. If you're needing practice for exam number 2, I would recommend that you practice. Look at or follow the link that is available to you on the D2L website. And as I mentioned at the beginning, there is an additional piece to the topics for exam number 2, and that will be homeworks 4, 5, 6, and phasors. So be able to play with, essentially, when you see these problems, think in terms of resistors, but now your resistors are complex numbers. And however you would analyze that problem with a resistor there, just replace that resistor with a complex number and do the math. What you need to be comfortable with is then performing the math steps necessary when dealing with phasor problems. And that allows us then to algebraically solve these sinusoidally excited circuits versus having to do it in the time domain. We can go into the phasor domain, play with algebra, and then back that out back into the time domain when somebody says, what? 5 at an angle of 30? What is that? Oh, that's 5 cosine omega t plus 30. You can take it back into the time domain. We'll get there at goal number 4. There's more than just 2 goalposts in this class. There's 4. Goals. First, let's review power and energy in an ideal inductor. Then we'll go through an example dealing with power and energy. And then we'll combine inductors in series and parallel. And those you'll see combine like resistors. It's just now that you have this energy storage characteristic of inductors, and so instead of just Ri, you have L di dt, or you have integrals floating around, but they will eventually combine consistently like you were seeing combining series resistors and parallel resistors. Here's our review. We did this at the end of yesterday's class. ELI is our acronym for trying to remember the current voltage relationship of an inductor, an ideal inductor. We have V is equal to L di dt. If we know voltage and we know current, then we can find power. Here's the instantaneous power associated with that inductor. P sub L of t is the voltage at time t times the current at time t. And if we replace the current voltage relationship, or replace voltage's description in that equation in terms of current, we have L di dt times I. That's the instantaneous power. From that, we can actually integrate power to obtain the energy, replacing the L di dt I into the P argument in the integral. We now can find that we have L we're assuming is constant. We're assuming it's not a function of time. That now slides outside the integral. We have L times this integral of I di, or the integral of x dx, and that's 1/2 x squared. Or in this case, it's 1/2 I squared, which now allows us to conclude that the energy in joules at a given time t in an inductor, the energy stored, where's that stored energy? In the magnetic field. That now can grow and collapse with the power that you're delivering and the power that it supplies to the rest of the circuit. And that will then allow this energy to fluctuate in the magnetic field, or vary as a function of time. W of t is the variable that we're using to describe the energy stored in an ideal inductor. Making sure everybody's awake. So I just said it was 1/2 x squared. It better be, thank you, 1/2 I squared scaled by the proportionality term L. Thank you. That's what happens when you start doing these quickly. You forget to go back and put an exponent on certain things. But it's now 1/2 L I squared. It is okay up above, isn't it? Yes. Okay. Let's now use this knowledge of an inductor. Here we have a very basic circuit. We're simply applying a current through an independent current source to an inductor. The inductor is 10 millihenries, and we now are giving this inductor a trapezoidal current shape, applying that to the inductor, and we want to know what's the maximum power delivered to the inductor by the current source. And we know how to find the voltage given the current. So let's do that first, because we know if we have voltage and current, we can form that product to find the power. And what are we doing? Eli tells us the relationship between voltage on that inductor, that's this, is L di sub L dt. And the time rate of change of current, that's what's needed to establish a voltage across this inductor. And there's only certain segments of time where we actually have some time current changing with time in this circuit. In the first segment, and now notice the units on the horizontal axis or on the independent axis, it's now microseconds. We can now find the slope and that's going up 100 milli over a time interval of 2 micro. That's 50 something. The something is 10 to the minus third divided by 10 to the minus 6. We combine the exponents, and we end up with this being 50 times 10 to the third, or 50k for our slope. And that's useful because that's that piece in our voltage expression, or the way that the voltage varies with respect to current in this inductor. Or what is the voltage now between 0 and 2? We can take the value of the inductance, L, which is 10 millihenry, 0.01. Here is now the L, times di dt, which we just computed to be 50k. And now that's 50 times 10 to the third times 10 to the minus 2. Do all of that, and we end up with 500 volts. So our voltage is now 500. The slope was constant during that time interval, and now we know that the voltage dropped across that inductor from 0 to 2 microseconds is 500 volts. What's the voltage from 2 to 5? There's no change in the current, and that's what's required to establish a voltage across the inductor. We are seeing no voltage dropped across that inductor between 0 and 5. And then what do we have between 5 and 7? Sort of the negative of that pulse that we had at between 0 and 2. It's just the opposite slope, and now we can sketch that. Questions on our voltage determination? And if I of t had some functional form, you could differentiate that functional form. Here, it did have a functional form, something times t, and we could differentiate it to get that something. What's the power? Can I move ahead in chapter 6? Using capacitive sensor. Sorry, that's the practical perspective in chapter 6. Did anyone read that? All right, I'll give you a slight reprieve, but I wanted to be able to show the two, current and voltage, together so that we could now sketch the power. And I won't be able to do that on this scale, but I won't be able to do it on that scale either. Probably I won't be able to do it on any scale. How's that? Here's W. That's the power. And power is just V times I, which means that we simply do a point-by-point product of these curves to try to find the P of t expression. And while we're transitioning from 0 to 2, voltage is a constant, and it's multiplied by a linear change or a slope. So now we're just changing that slope. So we're sloping in the power from 0 to 2. And what's the maximum value we will get to is determined at those 2 points. The product of I and V at that particular location in time, or point in time. So if we now come back to this point, this is now I at 2 microns, which is 100 milliamps. Here is V at 2 microseconds, and that's 500 volts. We multiply those together, 0.1 times 500, and we end up with 50 for our wattage, and we were just sloping linearly up to that. And then after that point, the voltage is 0, and anything times 0 will give us 0 power. This now is our maximum power that we've now pushed in to the, or that the inductor is absorbing during this interval from 0 to 2. What happens between 5 and 7? What's the shape? Is that it? No. What is the shape? It's just a point-by-point product of at each individual time. At 7, we better be at nothing. At 5, what are we at? We're at minus 500 times 0.1. We're at minus 50. This shape now looks like that. And then our maximum power is going to be the 50 watts. You need to be comfortable with those concepts, and then you could find energy if you wanted to, and your homework assignment will walk you through those steps. You'll now have current, voltage, power, and then energy. You can integrate the area under your power function or waveform to obtain the energy. Let's now combine inductors in series and in parallel. We have the tools to be able to determine that. Suppose we now want to collapse this combination of 3 series inductors into one equivalent inductor. Each of these 3 inductors have an inductance of L1, L2, and L3 respectively. We know they satisfy Eli, and that means that V1 is equal to what is V sub little 1 equal to? Eli tells us, doesn't it? That's now L1 di sub L dt. What's V sub 2? Same structure, just different labels. One label is different. They're in series. The current is the same. So that now, if we wanted to collapse those 3 inductors, if we didn't need to keep track of V1, V2, and V3 independently or by themselves, we could just say, well, what's the equivalent voltage hopefully you can see, since they're in series, the current's the same. We differentiate the current. It's the same derivative in each of those three terms. We can factor that common term out, and we now can say, oh, we're simply adding those inductors to find the equivalent inductance of those three series inductors. And that's just how you combine resistors. You have three resistors in series. It's R1 plus R2 plus R3. Inductors add the same way with the same structure. Series inductors add. What about if they were in parallel? I already gave you the answer at the beginning of class because I said inductors behave the same in the way that they combine, consistent with resistors. You should start thinking, oh, I should be seeing this reciprocal relationship, and now we can see that if we simply realize or apply KCL. KCL on the right tells us that the current flowing through the equivalent inductor, L sub EQ, is going to be the sum of those three currents, I1, I2, and I3. That's KCL. And I1, I2, and I3, I'm neglecting the initial conditions, but you can't. If they actually exist, you have to keep track of them. But here, just to keep things clean, I'm not keeping track of the initial conditions. I just want to find the relationship between these parallel inductors. And you can see that since they are in parallel, the voltage across those inductors is the same. The integral of that voltage will be the same in all three terms. And that allows you now to factor out that integral and see what is scaling that integral. It's this sum of reciprocals. It's 1 over L1 plus 1 over L2 plus 1 over L3, and that must be then the same as 1 over L equivalent. That's now how we combine inductors in parallel. And you'll get an exercise in that on your homework. Let's move into the plus part of exam number 2. This is the plus part, meaning this will be a problem somewhere on your exam number 2, in addition to problems coming from homeworks 4, 5, and 6. This is the plus. And the reason for doing this is so that you don't have quite as much to keep track of when we get into Chapter 9. We already know enough to be playing with these ideas with complex numbers. Now the point of this is to just start becoming comfortable manipulating complex numbers. The other thing that this does is when we do get to Chapter 9, it simplifies the analysis. We no longer have to keep track of sines and cosines as much. We simply go into the phasor domain, the frequency domain, and play with complex quantities. And then when we need to go back into the time domain, we just perform the inverse phasor transform. That's this script P and script P inverse. We apply script P, or this phasor transform. That just means you're taking a sinusoidal expression, and now we have to be sitting down dining at the restaurant. We have to put our napkin to the side, and what do we put to the side when we do the phasor transform? What's not explicitly retained in the two middle terms relative to what's on the right in the phasor transform expression? What is missing? Which is what's on the side. We're throwing away the cosine. That's correct. And we're going to be consistent. We will just assume if you see a phasor, that corresponds to a cosine in the time domain. So that's on the side. Thank you. What I was trying to emphasize is what else is missing besides knowing that we're playing with cosines. The frequency, omega. We're sort of keeping that on the side, but we need to know omega. That's the frequency of this sinusoid, how it's banging up and down, what rate it's doing that, or the frequency with which it's doing that. That's what we're keeping on the side. If somebody now needs to find the impedance of a capacitor, you're going to have to tell them what omega is, unless they want that to be a variable. And now you're plotting something as a function of omega. But in general, you would have to be told or find it in your cosine expression. So when I now say go into the frequency domain and I give you a cosine, you better be able to extract the magnitude and the angle of that cosine. And you probably want to keep on the side, I'm kind of joking, but you need to keep track of the omega, because it might come into play at certain points in the calculations. Here we're just going from time domain into a complex number, a magnitude and an angle. And now I need you to be seeing this in a two-dimensional plane. When you see or hear magnitude, you think, oh, the distance from the origin, and then you also need to know what's the angle. And the angle, a positive angle, is measured with respect to the positive real axis. If I now say you have an angle of 135 degrees, which quadrant are you in if we go to our 1, 2, 3, 4 quadrant system? Is everybody clear on what I'm just talking here? But now when you see a complex number, and I said, oh, that complex number had some magnitude and the angle was 135, I know that angle's not 135. It was drawn in a hurry. That's about 120, but it's supposed to be splitting those two vertical and horizontal axes 45 degrees on either side. That's 135. If we said minus 90, where are we? We're in the imaginary axis in the negative side. This is now minus 90 degrees. And how far we are away from the origin is the magnitude. If we said we're at 5 at 90 degrees, we've just walked 5 paces up the complex axis. If we say, oh, it's 2 plus j2, then we've walked over 2 and up 2. And now we're interested in the hypotenuse of that right triangle if we wanted to know the distance we are away from the origin. Those are the ideas we need to be keeping clear. Now, first, let's just get comfortable with the phasor transform. If you're given v of t, little v of t in the time domain, of 6 cosine 20t plus 15 degrees, what's its phasor? And this, in the textbook, they might be able to boldface that. Here I'll try, I don't promise, but I'll try to put a bar over something that's a phasor. V bar. This is a capital V, it's a bold V in the textbook. That needs to be a magnitude and an angle. And what would capital V be consistent with little v of t in the time domain? What's its phasor form or phasor representation? This is not too difficult. And on the side, if you need it, That's 20 radians per second, which is 2 pi f. I picked a bad number if I'm going to be dividing by 2 pi, but you could find the frequency in hertz by dividing 20 by 2 pi if you wanted to. F would be in hertz. This is, so you need to get comfortable with omega is equal to 2 pi f, where the units on F are hertz or cycles per second. And that one's maybe easier to sort of think about, but omega is sort of spinning in your complex plane. You're going omega around the units, around the origin at that particular rate. That's the omega t. Suppose now example 2. Suppose omega is 100 radians per second and I, phasor, is 4 at an angle of 10 degrees. What's its time domain expression? What is little I of t? What's the script p inverse of phasor I? Can you write that down given this information in the suppose statement? Now we've agreed to be consistent that it has to be a cosine. So we can get part of that. If it was multiple choice and there was a sign in there, you could say, well, it's not going to be that one. What else is it going to have to contain? What's the argument of that cosine? No. I gave you omega, didn't I? I didn't give you F. So this is now 200. Oh, gosh. Just checking. 100t. That's what was on the side. And now you fill in the other missing pieces from the angle and the magnitude. And if you needed to create this in the lab, we'd probably forget the 10 degrees and just say, I want a frequency of what? Probably in cycles per second or hertz, you would divide 100 by 2 pi and get that. So now you divide a little more than 6 into 100 and get a number. And the magnitude would probably have to be specified in peak-to-peak values, which would be then 8. Let's go through some circuit examples. Suppose now that you're exciting this circuit, and this circuit, you better get comfortable with this circuit. This circuit is actually a low-pass filter. Now you know how to design a low-pass filter, a first-order low-pass filter. First order means that you have one energy storage device, and that's a capacitor. That capacitor now is helping you filter these sinusoidal waves that it's seeing being applied to it. And a low-pass filter, that just means that it favors low frequencies, it passes low frequencies, and it tries to attenuate or remove high frequencies. It's a low-pass filter. It's trying to preserve low-frequency sinusoids. You're told that the capacitor has a capacitance of 1/2 millifarad. We haven't covered capacitors yet. That's tomorrow. We have a resistance of 2, and we're applying a cosine waveform of 10 cosine of 1000t plus 45 degrees. we will learn subsequently, now I'm just going to give it to you, that the impedance, this is now, when we're analyzing this, this has now reached sinusoidal steady state. You can assume that that cosine of 1000t has been happening forever. And forever in electrical engineering isn't very long. It's 5 time constants, and you'll learn more about that when we get into the first order, second order circuit analysis. We'll learn about time constants. But let's just say our time constant is 100 milliseconds. We'd have to wait 5 of those, a whole half of a second, before we actually made it to infinity and we were in a sinusoidal steady state. Everything now is shaking at 1,000 radians per second in that circuit, and the fact that we have some energy storage in it by the capacitor is just going to shift those peaks and valleys relative to each other. So everything in that circuit now may not be aligned in terms of peaks and valleys. The voltage and current, they're going to have an offset in where they peak and where they have their trough. What we need to be able to do, here I'm just going to say on the exam, this exam, you will probably just be given something like this, although you may have to find capital V sub S bar. What is capital V sub S bar? You'd be told that, oh, you have one resistor equaling 2, and once we go into the complex, into the phasor domain, we switch from using R's to Z's. Now we're talking impedance, because it could be functions of frequency. So now Z sub R, that's our old friend. It's a real impedance. It's a resistance. That's 2. The impedance of the capacitor is now minus J2. And you can see that as a complex number. Where do you see that? Minus J2. Where is that in the complex plane? Two steps vertical down, right? That's where you would find that number. If I said locate this complex number on the complex plane corresponding to that capacitor, you would just be on the imaginary axis at minus 2. So it would be minus J2. Anytime you see a J, you're going vertical. Positive, you're going up. Negative, you're going down. That gives you your two-dimensional plane that's this complex field. What's capital V sub S bar? Phasor transform. We just pull out the magnitude and the angle of that cosine. And that's 10 at an angle of 45 degrees. That's now V sub S bar. We now have 10 at an angle of 45 degrees. And we want to find what is V sub 0 bar. If, why did we jump into chapter 9? Because jumping in now is better than jumping in later. Really. Okay, so where were we? If you didn't go into chapter 9, how would you solve this? And this is what you do. First you go, I don't understand what he's doing. He's got complex numbers. Okay, put on some filters and just say these boxes, these little impedances are now like what I used to see as resistors. And say, oh, if I just had 2 resistors in series with a source, what would I expect the output to be? Some fraction of the input, a voltage divider. Well, now just take off the training wheels and say, okay, now let's pedal and apply voltage divider with complex numbers. That means we would have for V sub 0 bar, that would be the impedance that we're trying to find relative to the voltage. We now have Z sub C over Z sub R plus Z sub C times V sub S bar. That's what you know from what we've done so far this semester. That's a voltage divider. That's V sub 0 bar. Now, here's the step that you have to be able to perform in 48 hours, is the complex algebra. Now just replace these Z's and V's with what they are as complex numbers. Z sub C is minus J2. Z sub R is 2. Z sub C is minus J2, and they're multiplying by, or being multiplied by 10 at an angle of 45 degrees. When we're multiplying and dividing, we probably want to have them written in polar form, in magnitude and angle. When we're adding and subtracting, we probably need them in rectangular form. And you need to be comfortable going back and forth. For this, we've got a division inside the square brackets, ultimately, and then we have a multiplication. So let's get that denominator that's in rectangular form. That's walking over 2 paces and then down 2 paces in the complex plane. Let's convert that to its polar form. We want, if we looked at the denominator, that's now 2 minus J2. But that's just 1, 2 minus 1, 2. That's down here. Here's 2 and here's minus J2. We want to now express that point. This is the real axis. This is the imaginary axis. We now need to find this radius and this angle theta. And that's just trigonometry. The hypotenuse of a right triangle is the square root of real squared plus imaginary squared, those two components. In this case, since it's at 45 degrees, that's now 2 times the square root of 2, and you can convince yourself of that. And what's the angle? We've gone down as far as we've gone over. That's now a 45 degree angle, and it's below the horizontal real axis. This is now at minus 45 degrees. That's our denominator. What's the numerator? If we wanted to rewrite this, this is that in rectangular form, 0 minus J2. But since we don't have a real component, it's kind of clean to find its magnitude and angle. Where is minus J2? What's the angle of minus J2? Minus 90, and we're just 2 away from the origin. We can now rewrite this expression for V sub 0. Can I get out of red? V sub 0 is now, what did we say? 2 at minus 90 degrees. The denominator we just found was 2 square root of 2 at minus 45 degrees. And that's multiplied by 10 at an angle of 45 degrees. And if it's, this is really 2e to the minus j90. This is 2 square root of 2 e to the minus j45. This is 10 e to the j 45 degrees. Why am I doing that? So that you'll feel more comfortable when I say, oh, we're multiplying, just add the exponents, or just add the angles. We're dividing, oh, we just subtract the exponent in the denominator, so we're just subtracting angles. And we won't do this middle step. You'll just mentally remember that that's what you're doing. And to deal with all the magnitudes, you just multiply and divide. We have a couple of 2's that cancel. And we're left magnitude-wise with 10 over the square root of 2. What's the angle? We had a minus 90. We're adding and subtracting angles. We have a plus 45, and then downstairs in the denominator we had a minus 45. You need to be comfortable with where those pieces came from. What's our angle? 0. It's now 0 degrees, and our magnitude is 10 over the square root of 2. And now we can go back into this was v sub 0 bar. We can now rewrite that in the time domain with our inverse phasor transform. We take the magnitude, which is 10 over the square root of 2. We've agreed that we're playing with cosines. What was the frequency? Well, we have to remember what was on the side, and that was 1,000. So everything's shaking at 1,000. It hasn't. This is a linear system, so everything shakes at the same frequency. It's now 1,000 t, and what's our angle? If we really wanted to be explicit, we could say plus 0 degrees. When it's 0 degrees, a lot of times they won't even bother. They'll just say 10 over the square root of 2 cosine of 1,000 t. Boom. Now you know how that voltage across the capacitor is shaking relative to the source that was shaking. The source was shaking with a little different phase. That just means that relative to the spot on the ground that you defined to be the origin, time t equals 0, now you had a little bit of an offset in your source. And now your output, which is across your capacitor, is right on your t equals 0 in terms of its ups and downs. Well, I know you had so much fun with that one. Let's do another one. And what do you want to do here? Now you're trying to find the current through the inductor. You're trying to find the phasor. Now I haven't even asked you to do the phasor transform and the inverse phasor transform. I'm just saying play in the phasor domain the whole time. Just give me the complex number I sub L bar. If you now said, wait, I'm not yet ready for chapter 9, how would you view this problem? As an R1 and an R2 in parallel with a current source. And what would you expect to happen? You put some current in and it has to decide, am I going down this path or that path? It has to decide how it's dividing, right? We have a current divider. We simply apply our known current divider formula, but now we use complex impedances. We use complex numbers. But now we would find I sub L. I sub L would be, I sub L is now going to be 4 over 4 plus J4, 5 at 0 degrees. And now you simply do the complex numbers. What's 4 plus, and now we're doing division and multiplication, so we probably want these in magnitude angle or polar form. That requires one conversion, the denominator, 4 plus j4. And do you see that now in the complex plane? You walk over 4 in the real positive direction, and you go up 4 in the imaginary direction. You're now a hypotenuse away from the origin. The hypotenuse is 4 square root of 2, and the angle, 45. You've gone up as far as you've gone over. Now you plug those numbers in, and you can find this I sub L bar. By what? Multiplying and dividing the magnitudes and adding and subtracting algebraically, appropriately, the angles. And then you have a complex number. That's all there is to it. Don't get too excited when you go into the phasor, the frequency domain. You know how to do it. It's just now you have to get a little more comfortable playing with more than just real numbers. Now you're playing on a plane. Now you're playing with complex numbers. Real part and imaginary part. So we'll pick up with capacitors tomorrow.